Hey, it's Alex Williams of the News Stack here live from Shanghai for day 2 of KubeCon plus CloudNativeCon Open Source Summit China 2019. Here with Kevin Zhu. Hey, Kevin, how are you?
Good. How are you, Alex?
Kevin is General Manager of Global Strategy and Operations at PingCAP. And Kevin, we last talked, I think it was an open source summit in Vancouver a year or so ago. And we were talking about the technology and that PingCAP really has been developing. And so I'd like you to tell us a little bit about it. So TikV, and maybe you could tell us about TikV, what TikV is.
Sure.
And also a little bit about how it's built in Rust. And I'm also curious about Raft, and I'll have some questions about Raft. But why don't you just give us a quick overview of PingCAP and the technology that we're talking about here.
Sounds good. So first of all, thank you again for having me on. Sounds good to be on the News Stack and to be live streamed. So a quick background to give people a little bit of context to the question. So TiKV actually, so that's the pronunciation of the project. Ti just stands for titanium, and KV stands for key value. So as the name suggests, it's an open source distributed transactional key value store that actually derived its initial design inspiration from the Google Spanner project. Right. And PingCAP is basically the company. It's just like any other venture-backed company that first led the development of TiKV, the project. And since then, we have actually submitted TiKV to the Cloud Native Computing Foundation. So that happened officially last year when we first talked. So that was like around August or so of 2018. It became a sandbox project. And then as of a month ago, so this is like late May 2019, it kind of rose up the level in a sense to become an incubating level project in the CNCF cloud native ecosystem.
Okay, so it relies on Raft, and maybe you could tell us a little bit about Raft and what is this consensus algorithm?
Right. So Raft is a newer consensus algorithm, and consensus algorithm in a nutshell, in like plain English, is basically how do you keep state consistent in a distributed system. It's pretty easy to keep state consistent in a single node system because there's just one node there. But once you start to add a bunch of nodes in a large system that scales horizontally, how do you keep basically your data consistent? And the goal of using something like Raft, which I think came out in 2013 in a Stanford paper that wrote about the Raft consensus protocol, the algorithm and how it works, is to help a distributed system do that in a safe, in a formally proven way. And the motivation of Raft itself is to make a consensus protocol that's slightly easier to understand and implement. Before there was, or there is, another consensus protocol called Paxos. I think that was first known to the world in 1989. It's a relatively complex way of thinking about consensus, but a lot of really large systems still use various versions of Paxos, Google Spanner being actually one of them.
What is the foundation for Paxos?
Right. I don't actually know that much about Paxos, to be honest.
But what is the improvement then that Raft provides? Is it that distributed manner that it allows?
So I think the way that Raft is being perceived is actually more understandable, quote unquote understandable, meaning that from a developer perspective, I can actually read the paper itself, the primary source, and then figure out, okay, how do I actually implement this in code? Right. And because of that promise, and I think in reality as well, a lot of open source or any distributed system have kind of tried out Raft, and it's been growing really, really quickly. So even within the cloud native ecosystem, etcd, for example, is one of the first projects that use Raft to do its own consensus, algorithm building or a consensus protocol. And we leverage a lot of what etcd has done actually to build the current version of Raft inside TiKV. And in a nutshell, it's basically a kind of a quorum-based protocol, so what it's known as. So basically, you have multiple copies of the same data, right, to give you high availability across different nodes. And then each of the replicas will vote for a quote-unquote leader, or leader election is how it's known, and the leader responds to all the traffic that's coming into the system, while the so-called followers are really just there to make sure there's high availability and there's multiple copies of the data, right? And that is on a very generalized level how that works. And then there's like a bunch of optimizations that we've done and other people who use Raft have done to make the system work better as the system gets larger. Because in theory, a lot of this could work very well, but as soon as the system gets larger, as soon as it starts to meet production level traffic and the stuff that you see in reality, it starts to get complicated, and then you have to optimize to make sure the performance work.
Is etcd a consensus algorithm?
It's also a database. It's like an in-memory data store actually, and it uses Raft to achieve its consensus.
That's correct.
Yeah.
Right.
Okay.
So then, what are the ways that that PingCAP has optimized TiKV?
Mm-hmm. Right. So one of the things that we are working on actually for the next big release for TiKV 3.0, which actually will probably come out in a few days. So if you guys are hearing this as a podcast form, it probably has come out already. And that is what we called multi-thread Raft store. And what that means is that all these consensus building, right? These election that we were talking about inside Raft, this is basically network traffic. Right? Like these little pieces of data, these chunks of data have to talk to each other to figure out who is the leader, who is the follower, and they have to constantly keep each other informed as to who is the leader, who is a follower. If the node goes down, you have to elect a new leader. So there's a lot of talking going on. And once you have a system that's large enough or has enough data, and therefore you have more and more of these so-called Raft group that have to, maintain consensus, then the traffic gets to be a lot. And then that could become a performance bottleneck for your entire distributed system, whether it's TiKV or some other system that uses Raft. So multi-thread Raft store is a way that is something that we've been working on to kind of make that performance bottleneck a little bit easier to deal with, to alleviate that bottleneck, so that all this traffic, all this communication between the Raft groups aren't going to become an issue when it comes to operating the system at scale.
So how do you then compare? So how do you think about that from a security point of view? Then how do you, performance and security? There's always a trade-off.
Right, exactly. So we use gRPC as the kind of the RPC layer to do the communication, and we rely on the gRPC project quite a bit to make sure all that communication is secure, right? In between, or kind of like in between the cluster nodes that's within TiKV, and then you kind of have like your firewall around the whole entire system that lets you, maintain security as well. So I think multi-threading and then batching a lot of this communication could be helpful actually to maintain security, because the less you have to kind of, the more you have to reduce your surface area, essentially, the easier it is to maintain security.
So tell us then a little bit about TiDB.
Right. So TiDB is a separate open source project that works really well with TiKV to give you a relational database that has the horizontally scalable attributes of a NoSQL database. And now people call it a NewSQL database. It's kind of where that newness came from. Right, and TiDB is essentially a stateless SQL layer that is number one MySQL compatible, and that was a conscious decision that our team made to help the MySQL users first with their scalability problems. And it's a stateless set of servers that translates and processes SQL queries essentially, and you generate optimizations and query plans, and then you send that query down to the TiKV nodes where the data is actually stored and persisted. So TiKV kind of holds all the data as your single source of truth, and then TiDB is that layer that speaks MySQL. If you're a MySQL user, then that's a very nice way to use this distributed database, because number one, you don't have to change your behavior very much if you're an application developer. You don't have to change your code very much in most cases, because the compatibility coverage is quite good. And you get to use the same features that you like to use in MySQL, but now with this combination of TiDB and TiKV, you don't have to do manual sharding anymore, because the data is automatically broken down into pieces and then replicated using the Raft consensus protocol, and also maintained strongly consistent for you to consume.
So why was it built in Rust?
That's a really, really good question. And it's really like an early bet that we've made in this language. So TiKV, the project, started in, I think, April 2016. That was before Rust, the language, even became 1.0. So it was a bet that our team made because Rust had a lot of number one, had a really strong community. So it was loved by developers, even when it was a lot less mature. And also the characteristics of the language was very much needed for us to build a high-performing storage system, which is what TiKV is. So it does not have garbage collection. It has very strong memory safety features. And these were some of like the promises that was there that is now actually delivered, right? But at the time, we're like, okay, this could be the next thing. And we wanted to use something that is actually suited to the purpose of this particular layer that we want to build, which is a high-performing, consistent storage system. It probably wouldn't actually make sense to build it for some other thing that we were building, like the TiDB layer, for example, which you don't actually need a lot of that stuff. But that was the early bet that we had in Rust. And because Rust was so young, and still is young at this moment, we had to build a lot of libraries to support our own usage of Rust. So we had to build a Rust Prometheus library, we had to build a Rust gRPC library, we used the RocksDB storage engine, which is like a Facebook open source project. So we had to build like a Rust wrapper around the RocksDB library, which is written in C++. And that was for ourselves. But one really cool thing is that a lot of larger Rust projects now are using our library, including the new Facebook cryptocurrency Libra project.
Interesting.
Which is certainly not something that we've intended, but because Facebook chose also to use Rust to build this, stablecoin, or I don't know how you want to call it. I haven't spent that much time thinking about it. But what I do know is that they're using libraries that are built by PingCAP engineers for the purpose of first building TiKV, but it's now obviously widely available to all Rust users. So that's really cool.
Yeah, Rust is built on the principles of safety first.
Exactly.
Right? And so did that have an influence in your decision making? It must have, because TiKV is ACID compliant.
Right.
Right.
Correct. So that was probably one of the biggest reasons why we wanted to give Rust a shot, essentially, to be like, hey, if this is the promise that this community can deliver, we want to be a part of it. And this is a very important requirement for us to build TiKV, because it's not like any other key value store or other NoSQL databases that are out there. We've always built TiKV with the vision that this has to be strongly consistent first. It has to be ACID compliant first before it does anything else, right? And whatever performance trade-off that could happen with that, we are willing to take it if we can ensure that, because we're never going to build a so-called eventually consistent database like so many of the other ones that are out there.
What are the databases that are eventually consistent?
Like MongoDB, for example, or Cassandra, and they don't guarantee strong consistency, right? And that is just another characteristic. And if you're willing to live with that, that's fine. But for us, we wanted to build a distributed system that guarantees that consistency, because the original vision and the current vision still is to have a single source of truth, right? First. And that's how a lot of our users are perceiving TiKV, as that database layer that can give you that single source of truth, so you can feel very confident building other stuff on top of it, which a lot of companies and open source projects have now done, now that TiKV is in the CNCF's purview and things like that.
And ACID compliance, for those maybe not familiar with the concept, really is a foundation of database development.
That's right.
From its earliest days. You cannot really, a bank cannot use a database unless it's ACID compliant, because it basically has that capability to make it consistent. So when you're doing, for instance, an online transaction, or you're like balancing your checkbook online, you need to have that consistency so the numbers essentially add up or subtract or whatever it is.
Right. And you want to have that single view of that consistency throughout your entire system, right? As you add more nodes to your cluster, as your data sets grow, you don't want to compromise on that. And that's where Raft comes in for us. That's where all these other decision point comes in for us when it comes to the design of TiKV, because like you said, you don't want your bank account number to be wrong, right? No one wants that.
Yeah.
You don't want, I mean, even on like a lesser perhaps consequential but still important example, even like your Amazon orders, you don't want that to be wrong.
No.
And that has to be consistent all the time.
So let's move to the enterprise, but also think about it in the context of China, and
Right.
why we're here, and we're here in Shanghai for the KubeCon event. And so I'm curious on how you see TiDB and TiKV working together among enterprises, but maybe in particular what we can do is look at that in context of the China market itself.
Sure. So the interesting thing about the Chinese internet economy is that, number one, it has the largest number of internet users of any country, period, I think, right? It has, to my last count, 800 billion people, which is what, like 2.5 times the entire population of the United States, give or take, right? It's probably more now by the time we're talking. And not only are they internet users, they are mostly mobile internet users at this point. I do remember when I was much younger, I come to China to visit family, I would have to go to like internet cafes, and there were like these rows of desktops in like a dark, dingy basement, and I get like my instant noodles and I play Warcraft, right? Those days did exist, but not so much anymore. Everything is on your mobile phone, right? There are many mobile phone vendors. Everyone's doing it on your smartphone. I was visiting my grandma a week ago, and I was teaching her how to use her mobile phone on WeChat to order delivery on this other app called Meituan, which is actually one of TiDB's biggest user now, right? And the characteristics of that kind of internet economy is that the kind of traffic patterns you see are different. The kind of scalability and the demand for throughput in the sense of queries per second that your system has to process, or transactions per second that your system has to process, and the constant availability of this service that you have to be maintained basically 24/7 throughout. All that requirements are basically kind of pushed out of you from the characteristic of this internet economy. And a lot of people, they talk about, how big the Chinese economy is. They talk about valuation. They talk about stock market. What I find fascinating from like a developer's perspective is what kind of technical solutions can you come up with to absorb all this demand, right? And that gave rise to things like TiDB and TiKV, which is by nature scalable, right? And we are able to, we made the SQL processing layer, which is TiDB, and the key value storage layer, which is TiKV, separate. So they're two separate code bases, because you can actually scale your throughput much easier by just scaling your TiDB server as stateless, nodes. So you can, expand and contract depending on the kind of traffic patterns or promotions or whatever other kind of things that you as a company might be running. And that's hugely flexible and helpful because they do have these crazy, online shopping days, right? Like the most famous one is like Double 11. That is pioneered by Alibaba, but now everyone is like doing it. That has just, billions of dollars in transaction value on that one single day, which is kind of ridiculous if you think about it from a money perspective, but even more ridiculous if you're like the engineer who's working on the back end trying to make sure your service doesn't go down when you do have all this traffic come in. So in my perspective, all that demand is pulled out of you, right? That demand for better innovative technology is pulled out of you from the characteristic of this economy, which is really interesting.
So with an economy like this, it works at scale with using the internet essentially, then what are the challenges that are facing providers like your customers in China as the scale out continues?
Right. So there are a couple of, I guess, from a more user-facing perspective, problems that we are solving for them, right? One is just the sheer capacity that you have to be able to produce to absorb these services, whether it's my grandma or like your, taxi ride or whatever. It has to be on constantly, right? And the nice thing about a distributed system is that it is supposed to be highly available. It's never supposed to go down, right? The service can always be processed. There might be some, shakes here and there depending on your node quality, or maybe nodes always go down, right? But the system itself can handle a lot of that without human beings having to intervene. And that is a huge selling point for something like a TiDB, TiKV combo, because your operational cost from the end user goes down dramatically. And we've seen that because you don't have to manually think about and kind of fix or monitor. Well, you do have to monitor, but you don't have to actually like intervene manually all the time to kind of fix that, because the system self-heals itself, right? So that, I think, is a huge
The self-healing
capability. And you do have to tolerate some fluctuation in there, right? It's not just going to be smooth sailing, but it's so much better than your system actually going down. You have to send up a 404 message or a page, and taking 10 minutes to even bring it back up could mean up to literally millions of dollars of transaction values lost, right, on your system, depending on how large the company is.
So testing becomes critical.
Testing becomes really critical, right? I think we do go through very rigorous POC processes with all these companies, and they really help us improve the system too, because it's actually really hard to imagine how complex the traffic could be unless you've experienced it. So working with these companies to battle test your technology is really, really beneficial for the technology builders themselves.
Yeah, you discover things.
You discover crazy things that you cannot actually imagine in your own office, thinking of like a test framework.
Like what are some of those crazy things?
Well, I can't really share a lot of those things in specifics because they're kind of like specific to certain companies, right? One thing we do is that we actually use a lot of chaos engineering, for example, that leverages a lot of the stuff that we see from our customers' traffic pattern. We put that into our own chaos engineering framework. And for those of you who aren't familiar with the term itself, it really just means you do crazy things to your system to see if it breaks.
Yeah.
Right. And we actually automate a lot of that kind of fault injection. We use a lot of framework to automate and to come up with crazy scenarios, and to randomize a lot of these problems that could happen, to constantly test our software. And a lot of how we come up with that is by observing how our customers are using our software and the kind of patterns or just unpredictability, right, that could come up.
Yeah, for those of us who remember the earlier days of Netflix on AWS, they pioneered the concept of chaos monkey, right? Essentially letting out the monkeys into the system and seeing what havoc they can create. And so this is becoming a important matter as well, and it probably has been for a while. Right,
and it's good to have that as probably part of your standard QA process too, because you will never actually know.
So what's looking forward to TiKV and and improvements that we should be seeing made in the technology, some of the next hurdles you want to jump over. TiKV now is in incubator status at the CNCF, which gives it, I think, some more status and funding, I believe, right, to some extent.
I don't know about funding. You have to ask the CNCF guys.
Support, but I mean, more support, maybe not funding.
Right.
So what does that mean for the project? What does that mean for how we should see it being developed? What should we expecting over the next several cycles?
Right. So the first thing is, the big 3.0 release that we're working on to come out soon with more optimization inside Raft. But the interesting thing with how TiKV is interacting with other CNCF projects is that we use a lot of it for our system, right? So like Prometheus, like gRPC, another big improvement that we will probably have as part of 3.0 is kind of like batch messaging of gRPC messages, because like I said, all these communication with Raft and other parts of the cluster, that's all gRPC. And the more you get, the more traffic it could produce and more performance bottleneck it could form. So we're working on that, and that will probably be part of gRPC as well, right? So other people who use gRPC can take advantage of what we are doing for TiKV for their project. And the nice thing now for being an incubating status project is that, number one, I think being sandbox, my interpretation is that you're a project that could live within a year, might not, but we will give it a shot. We'll take you into the CNCF arm and we'll see what happens. Incubating to me means this project, this technology will be around for a long, long time, right? Whether it's CNCF helping it out, whether it's PingCAP, whether it's other companies and institutions committed to contributing to its growth, it's going to be around as an open source project for a long time. And that would, number one, I hope help it become even more widely adopted as a piece of technology. Our vision to donate it was to have this be a building block of other systems. And we are already seeing that happen because of the extra exposure, but also the neutrality of being a CNCF. I think, to my knowledge, there are at least 3 Redis open source layers that are built on top of TiKV. So people who want to use TiKV with a Redis layer on top to speed things up and stuff like that. And that's none of our doing. It's just people started doing it.
People just doing it.
Right. I think there's another thing called TiPrometheus, which is an official TiKV Prometheus binding that is part of the Prometheus documentation now. That's none of our doing. But I do think being part of CNCF, as we kind of move up the level, so to speak, more and more people are feeling comfortable relying on this piece of software to do other cool stuff with it. And that's really, really awesome and very validating, right, for our engineers and for our team who have been doing this for the last 3.5 years now.
Kevin, thank you so much for taking some time to talk with us here at KubeCon plus CloudNativeCon Open Source Summit China 2019. Wish the PingCAP team the very best. Wish you the very best. Thank you very much for joining us.
Thank you for having me, Alex.